about, you guys wanted to talk about machine design and robot and vibrations. So I found this video. Mark Rober is an engineer. He does a lot of YouTube content. He does a pretty good job of explaining things in a very simple way. So we're going to watch his field goal robot, and we're just going to talk about all the design he had to do for that machine. Then I found this other video about vibrations. It's not as good of a guy. I don't think he's kind of a little more boring. I don't know. I've never heard of it before. And then we have the liquid sand, which is also vibrations. So if we have enough time, we can get through everything. But if you guys have any questions, feel free to raise your hand and ask questions about any of this stuff, because that's what we want to do. We want to take it apart and learn about it. Yes, ma'am. Why sports? Because I like sports. And this robot, the robot doesn't have much to do with sports. It's just about the robot. Okay? So there shouldn't be too much involved with sports there. Any other questions you guys have before we jump right into it? Yes, sir.
Is this one kind of like vibration because it kind of spins its leg off?
Yeah, that's a good point. We can talk about that first. Yeah.
Like the rocket throwing.
No, I don't talk about machine design or vibrations, so that's why we can't watch the elephant toothpaste either. Okay, so if you guys are ready, no other questions then, we'll jump right into these. Try and keep it down, pretty quiet so we all can hear, okay? And we'll jump right into these. If anybody else that has a question, feel free to raise your hand and we'll pause it, we'll talk about it, but if not, we can jump right in.
This is Matt Prater. He's the place kicker for the Detroit Lions. He holds the NFL record for the longest field goal ever, which means he's really good at kicking footballs. And this is a robot I made, which, not to brag, is also really good at kicking footballs. So to settle who's better between the two of us, we're going straight to Detroit. Mano a mano, man versus machine. But to do that, I'm gonna need an 8-second travel montage. Experience, and so I could soak up the fact that I had an entire stadium just to myself in the most professional way possible. We just got word Matt is about 10 minutes out. He thinks he's coming here just to teach me all about like the kicking mechanics and the science behind kicking field goals, which is partially true. I am curious, but the real reason I'm here is I built a machine that can kick really far field goals. I think it can kick it farther than any human. But if I'm really going to test that hypothesis, I need to be kicking against the one human that can kick field goals the farthest, and that happens to be Matt Prater. Originally, a guy named Tom Dempsey, who had a unique kicking foot, held the record with a 63-yard field goal, and no one could beat that for 43 years. But then Prater came along and beat his record by 1 yard with a 64-yard field goal in 2013. And he still holds the record nearly a decade later. There he is. And not only did Matt show up, but to my absolute delight, he brought along his personal trainer. Who's this?
This is Max.
What up, Max? How are you, buddy? And so after I joined him for his standard warm-up and stretch routine, I went straight for the jugular. So do you practice just as much as everyone else on the team?
I definitely don't practice as much.
Everyone on your team is watching. It's like, ah, he's fine.
But he wants to be the kicker until it's the end of the game and you need to field goal.
Then I asked him how to kick really long field goals, and he said it all comes down to just two things.
Leg speed.
Leg speed.
First.
And leg speed makes intuitive sense, but then he told me the second critical factor is making contact 2.2 inches up from the bottom of the ball. Extensive research has been done that backs up these two factors as the most critical for maximizing distance. So after that, he showed me the proper technique to achieve those two factors.
So you come at an angle so your plant leg should be as close to straight as you can, and then at this angle, so your kicking leg can be straight. So right when you're making contact with the ball, your kicking leg should be locked right at contact.
And where do you hit the ball?
So you'll hit the ball, you know, the little bone right in the middle of your foot.
Yeah, like right here.
Right there.
This will be the first time in my life I've legitimately attempted to kick a field goal. But after Matt's coaching, he made it seem like it was pretty similar to playing soccer. And I like to play soccer. You shouldn't have done this, but you taught me everything you know. So I say we have a competition, me versus you. I thought as a wager we could have that Gatorade thing. It's got ice water in it. The loser gets dunked.
All right.
You okay with that?
Yeah.
You seem pretty confident.
I don't know. We'll see.
Look at this guy sandbagging. So with that, we were ready to go, and this was his first kick, which he lined up left-footed, which didn't go well for me, because he's not left-footed. This is a disaster. And then it was my turn. All right, Rover. Nope. Laces out, Dan. Gotta remember everything you taught me.
Yep.
I like that.
Got it.
Nailed it. Moving back 5. This is a 25-yarder. They might say, Mark, what do you mean 25? You're only on the 15-yard line. And that's true, but the end zone itself is 10 yards, so you always include that with the kick distance.
Got it. Good shot.
All right, Prater, let's see what you got, pal. Ignore this. Don't let this bother you.
We can have a full conversation.
Would you ever break this? Oh, goodness, that was right in the middle.
Oh, that was a bad kick, but I'll take it. Got it.
Got it! Okay.
Bomb. Crushed it.
Oh, wow. So far, this is pretty similar.
And just kicking field goals. That's funny. It's very funny.
Why did you put it in like any?
We'll go right here.
You never saw this coming, did you?
No. It's honestly the last thing I expected you to do.
And in my defense, this was a super popular kicking style in the early 80s. But with no proven advantage, no one really does it anymore. Except for me.
You did.
Oh, not cool.
That's the worst sound you can hear as a kicker, too. Hitting the pole, yeah, or crossbar.
Oh, that was heart-wrenching. At least the high speed looked kind of cool. And so here's Prater for the win. And just the perfect form. All right, Matt. I thought the barefoot was going to be my trump card, but I'll concede. As it stands, I'm getting the Gatorade bath. But while I might not be good at kicking footballs, I am good at engineering, which technically means I'm really good at kicking footballs. Let's go, baby!
What is this?
Okay. And stop. This, now you can come around back. Greatest kicker of our generation.
Oh, no way.
You're looking for Ray Finkel?
Oh my.
And the clean curve shorts.
So now Prater knew the real reason I was here, but to truly understand what he's up against, we have to go back just about 1 year, because that's...
So he says 1 year, so that's how long it took him to make a robot just to kick field goal.
It's kind of stupid how you.
You're right, but he makes lots of money, so he can do whatever he wants. So, your guys' robots that you made, that you designed, right, they do some pretty complicated things, right? The easiest one here, I think, goes to the kitchen, picks up a sandwich, and takes it back to your
That's
room.
mine.
That's super simple that's super complicated, compared to kicking a field goal, right? There's a lot more going on there. And some of you have super complicated ones that like freeze-dried food and flew it to Africa. So just think about if this took an hour, like 1 year to make, how long would yours take to make? You know?
With the help of my buddy John here, we tested our first prototype. John's really good with this kind of rugged, high-strength build, because he's worked in the industry doing props and special effects. And so at the end of that first day of testing, we could make a 60-yard field goal, but honestly, it was kind of just barely. We needed more power and accuracy because it was really inconsistent. But to understand how we fixed it, first you need to know how it works. Fundamentally, we've got a hub attached to an axle here. It can freely rotate, and if you slap a kicking leg on the end, they both rotate together. Then if you put a winch on this side connected to a wire that secures to the hub here, and then springs on this side also attached to a wire that attach to the hub in the same spot, then when the winch pulls down, the springs stretch out as the leg is cocked back into position. Now we just need a way to fire the thing. A quick release is a hook system that easily unhooks when you pull a cord. So if we put one of those here and then pull the cord, the springs now contract, which makes the leg spin real fast. For version 2 of the robot, everything had to get much more rugged and compact because we doubled the force from the springs to over a ton. And when we went out to test this time, it definitely did have more power, and our 60-yarders were looking much more promising. But because the football was making contact off to the side of the leg, it still wasn't as accurate as we wanted. So for version 3, we changed how the foot attached, which allowed us to hit the ball straight on. We also tried to determine the best foot diameter, as well as the best spot to make contact with the ball. But I still wanted even more power, which was tricky because there was already so much force that we busted our industrial.
So you can see here, this is their 3rd generation machine, right? So they fixed it up, they made it even better, and it still breaks, right? It literally breaks. You can see, just highlighted this bolt right here just flew off. So then machine design, you're always trying to get better, right? So here he's trying to get more and more and more power, but as you do that, you realize a lot of things have to change in order to make that happen. Okay? So that's part of machine design, and as you go through that cycle that we talked about, where you find a problem, you imagine a solution, you try and make a prototype, and then you test it, and then you see if there's a problem. This cycle can kind of just keep going on and on and on and on.
Material strength quick release, which is why there's a loose bolt in the frames here, which is just never something you want to see. And so for the 4th and final version, we upgraded to a much beefier quick release, and then increased our spring force to 2 tons. We also got clever with some mechanical advantage by making the diameter of the leg sprocket twice as small as the driving sprocket. So it rotated twice as far, but in the same amount of time, which means we doubled the speed. With a big build like this, you are only as strong as your weakest link. So this process of prototyping, failing, and fixing helps flush out all the weak links as quickly as possible until hopefully there's none left. And so a year after we first started, this 4th version finally had the kind of power and accuracy I was hoping for, even if we were definitely pushing the physical limits in a few critical spots. For now, though, it was time to give Mr. Prater a proper introduction. So Ray Finkel is my surrogate. This is what I couldn't do even with my bare foot. See if old Ray here can do better. Now, I'm not abandoning everything you taught me here. Okay, a few steps over. Okay, here we go. You ready? 3, 2, 1. Get up! That's my boy! That's my boy!
Oh, that looks really easy.
That looked pretty easy,
that was
yeah.
really easy.
I hate to tell you that, but that wasn't full power. In fact, that was only 1/3 power. For a half power demonstration, we went to the extra point location where, for reference, here is Prater, the mere human, kicking full power into the net, and then Finkel at half power, kicking it into the stands. And at this point, we poked the sleeping giant, because first of all, Matt suspiciously asked me to hold his next kick.
It's time to help your customers save.
Compound W helps clear warts away fast to
And secondly, after that 50-yarder, he continued working his way down the field, despite my best efforts to even further rig the competition.
Oh my god. You're real bad golf etiquette.
I had this great idea to arrange with my buddy Paul Nergala to get some drone racing footage of a field goal because he's the drone racing world champion, and that would just be so dope. This footage here is from a test session we arranged to see how cool it would look, and it turns out the answer is really freaking cool. But after we got everything set up, a staff member requested we didn't fly drone inside, so you're just gonna have to use your imagination as Prater bombs this 60-yarder. Which meant the next kick attempt would be farther than his NFL record. And one of the things Matt does so well is that technically you want to launch the ball at 45 degrees to maximize the distance on a kick. More than that, and you waste your energy in height. Lower than that, and it hits the ground prematurely. In real life, though, where the ball experiences drag from wind resistance, the ideal angle is closer to 40 degrees, which you can see Prater has down to a science. This is 1 yard past the NFL record, which this man holds.
Get up, mate. Get up.
It's good!
So, 65 yards is 195 feet for those of you wondering. So it's very, very, very impressive. So that is as far as
You're crazy, dude! I'm putting on my rally cap for you, buddy. As much as I don't want to get doused with Gatorade. And while Matt's taking a few attempts at this 70-yard field goal, let me just say that it's really special being in the presence of an elite athlete such as himself. Don't rule out barefoot here. You know what I mean? Oh my goodness. These were honestly the first shots he missed all day from anywhere on the field.
No.
Dude, well done. So now that Prater was unsuccessful from 70 yards, Finkel rolled over to potentially win the competition and save me from an ice bath. All right, here we go. A little bit of train horn for good luck and good measure. And this is where Matt got a little taste of Finkel's true range of motion. This is about 80% full power. That's all you gotta do, dude. That's all you gotta do. 3, 2, 1, hit it! Go, baby, go! And so even with a terribly inefficient launch trajectory, we'd settled the question of man versus machine. That's my boy! That's my boy! Finkel! The hang time, though, right?
So high. I think it was gonna get there. Really.
I know. But since Finkel had made the trip all the way out here, we decided to keep going and try his foot next at an 84-yard field goal, which is an even 20 yards past the NFL record. But first, we wanted to try and figure out the foot speed of Finkel versus Prater. So we recorded a few kicks in slow-mo with a checkerboard background behind it. This is a trick I learned while at NASA that they've used for ages, because if you know the size of each of those squares, it allows you to watch back the clip and tell the speed of any moving object in the footage by converting grid boxes per second to miles per hour. So when you do this, you find Matt's foot is moving at an insane 48 miles per hour, which puts him right up with the elite place kickers and soccer players. The robot's foot, however, is traveling more than 30 miles an hour faster at a blazing 82 miles per hour. We also measured the ball speed after contact, and while Prater is at 80 miles per hour, which is again insanely fast, the robot clocks in at 120 miles per hour. And that checker background speed trick is so cool that I invented this. I call it the putty on your percent and 120. Alright, it's 7. It's great. The RS per hour. Here was his first attempt from 83 yards, although still not quite at full power, and I'll explain why in a second. Okay, a little bit of horn. Now we're ready. 3, 2, 1. And when you see this, these balls were no Deflategate Brady specials. These were the most inflated footballs I'd ever handled. You could barely dent them in with your hand. It's just the pressure from the robot foot was that high. The first kick had the worst possible trajectory, and so the hang time was hilarious. We had quite a bit of energy up in the air. I think we need to optimize this a bit. But straight is a gosh darn error. So for the next one, we arranged the foot to contact higher up on the ball so it wouldn't pop it up so much. But still not a full power kick. Go! Please! But this one was just short because it knuckleballed and didn't pop up high enough. So now we knew exactly where to strike the ball to split the difference between those two, and we figured we might as well leave it all on the table and go full throttle. Which makes now a great time to explain why we weren't just doing this on every kick. On our last trip to the practice field, we were totally dialed in, as you can see here. I mean, that thing is suborbital. As a reminder, this is a 60-yard attempt. This is only 4 yards shy of the NFL record. And as you can see, we've got a little room to spare as we pass through the uprights. So then just for fun, we opened it up and sent all 2 tons of spring force through the machine and into the ball, which is when this happened. We're just going absolutely full, all of the power. What? Oh my God. As you watch that clip back, the ball landed here, but it had the height to clear the uprights right here. And you'll notice that's right above this unique pattern in the cement. And from the satellite view, that unique pattern is right here. Now we were kicking from the 50-yard line, so the question is, what is that distance? Well, if we borrow this convenient 100-yard measuring stick, then that kick would have gone through the uprights with no tee and a slight headwind from 105 yards away. Now this is a bit of a good news, bad news situation, because on one hand, the ability to max out the robot and kick 105-yard field goals is amazing. But on the other hand, on the very next kick, this happened. have the key in the key shaft because of the whole 2 tons of spring force thing. And in case you're familiar, this is the key. It's just a chunk of metal that gets wedged in here so that when the key shaft turns, the sprocket turns with it. So the final improvement would have been to swap the key shaft with a spline shaft because those distribute the load evenly among many surfaces as opposed to just one. Unfortunately, those spline shafts had a 2-week lead time, and we were flying to Detroit a few days after this.
Right, Finkel, from 83 yards, full power plus a little more. 3, 2, 1.
Oh! Oh! Oh!
Watch Finkel's head here. I'm sorry, buddy. And sure enough, it was the key that was the culprit.
Keys aren't supposed to do this. Like, that's bonkers.
And so despite the explosive finale, I'm calling this a W. Not only did Robot Ray Finkel beat the NFL record with a 70-yard kick at sea level with no wind, but he did it at 80% power and a super inefficient kick trajectory. On top of that, even though he lost a couple freaking legs in the process, he showed he's capable of bombing a 105-yard field goal into a slight headwind right off the turf with no teeth. And so with all that, honestly, I was willing to let Prater off the hook, because an argument could be made that I technically sort of cheated. But his son Pax was already way too excited about the prospect, which I thought was just fantastic, until it turned out he got off easy by comparison.
All right. Any questions? Yes, sir.
How was it able to bend that just jumped from metal?
So it was 2 tons of spring force.
Yeah, that's a car.
Obviously more than the metal poles before it got sheared. So you guys remember when we talked about shear stress? So obviously that metal cannot withstand 2 tons of shear force in that way. Yes, sir.
Why didn't the kid just
Can we get a little quiet while I answer questions here, guys? Sorry. Go ahead.
Why didn't the kid just pick up the whole thing in Gatorade and then?
I think it's a little heavy for him, probably. Yes, sir.
Doesn't the rocket powered scout golf club have a bunch of shaking? What was the other?
Vibrations?
Yeah, vibrations.
We probably could. Yeah, that one might be better to look at than the liquid sandbox if you guys want to.
I was watching a little bit of it. I was watching a little bit of it like yesterday or so.
Sure.
And he said that most of the time he cut out a bunch of the nitty-gritty machine design stuff. But he said that in that video yes, there were watermelons exploding, but he put in all the machine design nitty-gritty stuff.
Cool. Yes, sir. No, because that's not part of it. Because we already went on machine design, now we need to move on to vibrations. If you guys have any more questions. Any other questions that we have on machine design? Okay. So he'd taken a year to design and prototype this machine. After 4 versions, it was still breaking. Okay, so technically he said there would be a 5th version if they had time to wait for the different gear system, the different key system, but they didn't have time for it. So that's a year-long, 5 different versions of this machine to do something as simple as kick a field goal. Okay, if that gives you any idea of how complicated, how long, and how much time a machine design can take. Okay, so 1 year, 5 versions, lots of money, lots of time for something just as simple as kicking a football. Okay? Alright. Now this guy here, he's not quite as exciting, but the beginning of his talk is very good. We might not watch the whole thing so we can move on. But the beginning of his thing is really good. So try and listen to him. He's got kind of a heavy accent. Okay, so try and listen to him, try and make sense. We'll all have the captions up so you can hear him. But if you guys, again, if you have any questions, raise your hand, we'll pause it, and we'll talk about it a little bit, okay?
Dr. Andre Batacco joins us from Liverpool John Moores University to talk about the role of vibration in engineering.
You have 3 types of vibration. You have the torsional vibration, you have the normal spring or mass vibration, you have the pendulum, 2 types of pendulum here that you can use. All of them are based on vibration. So when we talk about vibration, it's a fundamental thing in life because everything we do is vibration. Whether I'm speaking to you is only vibration given to you so you can hear it, But your heart beating is also vibration because it's a period. For vibration itself, many people do not understand that everything in this life vibrates. Whether this table that is standing there, this thing that's standing there, everything vibrates. There's nothing as such that will not vibrate. Everything oscillates. There are some engineering applications which we want to do, which is more towards this standard we have here. We have this, for example, can be applied into oil drilling rigs. When you are drilling, there are a lot of vibration there. It's a big problem in research environment. And also you have this one, let's say you want to understand it. You have your car is on suspension, core suspension, they are all on that. That is where you apply this. This also an oscillating pendulum, also we use to teach that. Where can you see that? You see this in a big building. Take the tower in Dubai. How do you stabilize this building against the wind gust? You must have, if you look inside, if you go in YouTube, you find it has a huge pendulum at the bottom. These are all based on this system. We've got to understand the fundamental of this. Even you are in civil engineering, that principle comes in. So that is why understanding this is fundamental. You're driving your car. The airplane that is flying, if you don't get it right, and the wings start vibrating, you're out of control. That's why when you're in the plane, and they say, fasten your belts, you're entering the vibration. That is a problem, you've got to understand that. And the basic of it is on this. It does not matter horizontal or torsional, they're the same thing, the same equation. And what do you need to understand? Because if you let this to vibrate into something called resonance. Resonance is when the force of vibration matches your natural frequency. What is natural frequency? Natural frequency, let's say you're walking around on the street and you knock a lamppost, you will hear a sound. That sound is mostly based on the natural frequency of the lamppost. But you will see it. But that sound is vibrating. That is the vibration of the body that gives you that. So how do we look if we were to apply these three type of vibration in life? This is applying.
So now I'm just going to talk about examples of what each of these types of vibrations mean. I think it would be fun to look up. Okay, so what they're going to do here is glass, all things, okay, has a natural frequency, and that's the rate at which the molecules in something is vibrating, okay? So we know that if we look on an atomic level, all of the atoms, molecules, and everything are vibrating, right? In solids, they don't vibrate very much. In liquids, they vibrate more, and in gases, they're bouncing around all over the place, right? And so that vibration that they have is called a natural frequency. And you can, if you match that natural frequency with sound or something else, you can push that. So whatever vibration they have, if you match that with sound, you push it even further and further, and you can get it to a point where things will just break if you can match their natural frequency. So here, this is a microphone, okay, this is a speaker, and they're pushing sound out at the natural frequency of this glass. They're trying to match it perfectly, so they're changing the pitch. I don't think you can hear it in this. So maybe we'll see if we can hear it. It'll probably be really high pitched to match the frequency of glass, okay? But if you match it high enough, if you match it just right and strong enough, it can push those molecules out of formation with each other, and things will just break.
So it's so high pitched that you can't hear it.
Yeah, I think that's, or maybe they're just not putting any sound on their video because it's kind of an annoying, really high pitched sound anyways, but.
Yeah. You could also do that with cars.
With everything. Every single thing has a harmonic frequency, a natural frequency. And so it's not just glass. They usually use glass because it's kind of easy to do since it's so fragile.
What about us?
Yeah, we do too. Yeah. So I don't know It would be different for everyone, and each part of your body would be different. So he picked people's organs, so their organs would just explode like this. So it was very gross. Yeah.
Wait, wouldn't it have to go through your stomach? Yeah.
Well, because of the vibrations, it doesn't matter. The sound will travel right through you. That's why if you go to a really loud concert, there's those big loud bass ones, you can like feel them inside your stomach. That's because sound passes through your body. It's not hard for it to do that. And so it can get to any part of you. Yeah. Yeah, they must have the sound off because they must just not have any sound for this video. We can see it as another one. Yes. So this is a piece of paper that they put in here so that you can see how much it's vibrating. So they're just saying that loud of sound, even at the wrong pitch, makes it vibrate. Okay? Now they're going to change the pitch to match the natural frequency of the glass. So, like I said, kind of an annoying high pitched sound. It wasn't getting louder, they were just changing it. They were changing the tune that it had, the pitch that it had, so they were making it slightly higher. And then when you heard that extra vibration, kind of, that was the glass starting to vibrate too. You can hear as they change it slightly. Right there, did you hear that when it changed? That's actually the bottom of this glass starting to vibrate against the table because the whole thing is shaking so strongly. Right after that is when it breaks. So you guys have heard about like opera singers who can break glass with their voice? That's what they're doing. Is they're finding that frequency and being loud enough that they can just break things. So let's not try it here. We have very expensive glasses. So what this guy is talking about here, he says there are basically 3 different types of vibrations that you'll see in real life. This one here is torsional, and he says this is what you use when you're talking about drilling wells or oil lines or something like that. And so what you have is you'll have a really big motor, a really powerful motor at the top here, and it's going to spin that drill all the way down. As it spins that drill, there's probably a drill bit at the bottom to cut through oil, or like a pump to help pump water or oil up to cut through everything. If, however, you get something too strong for your drill to cut through, like granite or diamond even, if you got something really hard down there, this bottom part will stop spinning, but the motor at the top can be like 200 yards away. Like you can be very, very deep. The motor at the top won't realize, and so it will keep spinning, and this part will be bottom, will be stuck, and so you'll just twist your pipe here, this torsional arm, you'll twist it until you'll hear this loud pop, and you'll just snap it right in the middle, which obviously is very, very bad if this is like 200 meters deep, right? Because then somebody has to climb down a hole this big, grab that bottom piece, hook it up to something so they can pull it all out of it. So obviously you don't want to let that happen. So what they do is they have lots of sensors that will listen for the sound that the drill makes at the bottom. And when that drill begins to stop making sound, or it makes irregular sounds, okay, and you'll get vibration through this whole member here, then they'll know they need to stop the engine, they need to slow it down, or they need to speed it up if they get to something easier. Okay? So that's a big deal in oil digging and in oil digging and stuff like that. This middle one here is just on springs, so he compares it to the suspension of a car. Okay, so as your car goes over bumps and holes in the road, it starts to vibrate, it starts to bounce a little bit. If it keeps vibrating and bouncing, there are certain racetracks that are made this way to test cars, to test the suspension on cars, where they make the road look like this, to test the suspension of the car. Because if it goes too crazy, that car can rip itself to pieces because it's going so fast. What's that? Yeah, not good. vibration of that car on the washboard like that, it will rip the suspension off of the car. It's gonna be that crazy. And then this one here, the pendulum, we talked about this being similar to a very tall skyscraper, okay? So if you have a skyscraper and the wind is pushing super hard on that skyscraper, like we talked about, obviously it's gonna bend this way, and then it'll bend back, okay? If your building is not strong enough, or if it's too elastic, it'll just keep going and keep going and keep going. And if that wind is really strong in random bursts, it can rip itself apart too. Yes, sir?
There was a building in China the other day, like a few months ago, that just started swaying.
Yeah, they can be crazy. So we talked about one in one of my engineering classes. They had a really tall building, okay? And to make sure that this didn't happen, in the very top of the building, they'd have a big, heavy weight. It was springs on every side. And so if the wind pushed that building, the springs would push that weight back towards the middle to try and hold the building in place. So that this was the building and my head was the weight, it would look like this, to try and keep that building standing up straight. But if the power went out, then the springs on that weight would quit working the way they were supposed to, and so then the whole thing would lean even faster. And so they had to make sure that no matter what happened, that weight at the top would never lose power, or the building would crash like 5 times easier than normally. Yes, ma'am?
So, like, can, tsunamis be, like, vibrations?
Of course.
Because they have earthquakes.
Yeah.
I remember my mom told me that when she was in Russia, she was really close to, like, the sea, and, like, she was very close to Japan, and also, my grandpa was a merchant, so they would always be on the sea. They would always see, like, tsunamis in Japan, and they would always hear about it.
Yeah, for sure. So tsunamis normally come from earthquakes. That's normally where they come from. So what happens usually in earthquakes is the plates of the earth under the water, or anywhere really, they slip up somehow. So they'll slip like this, they'll slip like this, they can just move sideways. And when they move like that, all of the water above there kind of moves up with them. Okay, so it'll move up when that happens, and then they'll move down, because that's what water does, and it'll suck in all this water from everywhere else to fill that gap. And then when they come back up again, that water will rush out. And that's how we get tsunamis. It's because of earthquakes and stuff like that that changes things. So let's take a little look at this hot tub. Okay. So this is all about the vibration that the sand is going through because of the air and how that changes the properties of the sand. Okay. Shh, guys, pay attention. So this is a look at how something as simple as sand and air can change, okay, vibrations.
Solid sand. This is one of the coolest things ever. If you take a tub of sand like this, and then add it in just the right way, it basically becomes a liquefied soup.
Why is it so bad? Why is the video sped up?
So I was watching it really fast earlier.
And sitting in a hot tub filled to the brim with solid sand.
This is one of the coolest things ever. If you take a tub of sand like this, and then add air in just the right way, it basically becomes a liquefied soup. In science, this is known as a fluidized bed. It's used in industrial applications such as powder coat painting or in grain silos to make sure that the grain flows smoothly to the outlet. With air on, the top surface is nearly frictionless. It's like an air hockey table. And then when you cut off the air, it freezes everything exactly where it's at. focus yourself. And then because I became curious what it would feel like to be fully immersed in something like this, we made a hot tub size version. As you can see from the 60-year-old video from the Royal Institute of Science, this demo isn't exactly new. I've wanted to build one for a long time, but you can find literally no information online on how to make one like that. So I started combing through a bunch of patent drawings for massive industrial-sized fluid beds, and I noticed that instead of one big inlet, they all had a bunch of small holes to deliver the air. So starting with that in mind, it still took us 25 failed versions before we arrived at this.
So again, cool machine design, 25 different failed versions of something as easy as putting air in the sand. Okay, so, if you want to make your own, you definitely can, but might take you a couple tries.
This design. As you can see, it's just a bunch of half-inch PVC pipes arranged sort of in a ladder. But the key is to drill two 1mm holes 90 degrees apart from each other, and then do a bunch of those spaced 25mm apart. Then you glue all the pipes together and just make sure you orient the holes down so that will keep the sand from getting in. And then you just seal off the container with some hot glue. And then fill your container with either fine sand, or we found glass beads worked really well. And you can power it with a small air compressor like this, or you could just rent a large nitrogen container like this for about 30 bucks, and that'll give you 10 minutes of runtime. As usual, I'll put a link to all of the parts I used in the build in the video description. So my buddy Ken had an old broken spa in his backyard, which we decided to put to good use.
It just stops and you're like locked in place. It's like a weighted blanket on every surface of your body.
Now that it was tested and ready, in my ongoing quest to be the favorite uncle, I decided to surprise my nephews with it. But before we get to swimming in sand, let's talk about the science behind a fluidized bed. And when we don't, click away if you think science is boring. If you're new here, you should know that my approach to science is similar to Velociraptor hunting patterns. I try to bring people in with a catchy thumbnail or a cool thing to see, and then when they least expect it, and then the analogy breaks down a little at the end. But if you promise to hang with me for the next 2 minutes, I promise to try and walk the delicate line between trying to make things simple to understand without oversimplifying or being condescending. Fluidization is just when you have enough upward air so that the force of the air pushing on each grain of sand is equal to the downward force of gravity or weight. And when that happens on any individual grain of sand, it hovers in equilibrium like this. You can think of forces acting on an object like a tug of war. If an object is in equilibrium, that means there's a tie, and it doesn't accelerate in either direction, just like in a real tug of war if the sides are even. However, if you add Stone Cold Steve Austin to this side, that will make it totally unbalanced, and will start to move this way, which is actually what happens if you accidentally turn the air up too high. And so fluidization occurs in that sweet spot where the sand particles hover at equilibrium, which makes them easy to move around. This is also the reason sometimes you'll see pools pumped with air to cushion the landing for the divers. Now you notice that some stuff floats in the sand and other stuff sinks. This has to do with the buoyancy force, which is a function of the density of the surrounding fluid and the volume of the object itself. Whenever an object exists in a pressure gradient, there are forces from pressure pushing in on all sides, but they push a little bit harder the deeper that you are, which is why it hurts more to be the bottom guy in a dog pile, or it hurts your ears more the deeper you dive in the pool. And this makes sense because the deeper you dive, the more water there is above you pushing down. And if you add up the side.
So we talked about that a little bit at the very beginning of the semester, buoyancy force and the force of stagnant waters. We didn't go into it in super great detail because it's just a little bit beyond what we needed to do in this class. But this is a pretty good description of it, okay? So what he says here
the more water there is above you, pushing you down. And if you have
This picture right here explains that pretty much perfectly.
See that Mark Rober is smart.
Yeah, he's smart. I agree that he's smart. He's just not teaching this class. That's why I was. So this is pretty much perfect to show how the forces of fluids work. And the deeper you go, the more water pressure there is, the more force is put on you by that water. So that means if you are lighter than water, it will push you up. Okay? So humans are about 70% water, but you also have a lot of air in your lungs. And so because of that, you're lighter than water. You should float, but it might not be at the very surface. You might float down a little ways once the pressure of the water becomes stronger enough. Okay? So that's why most people have to swim. But people who are very buoyant, which means you have a bigger volume, but you're not as heavy, you will float easier. Yes, ma'am.
So I have this 6-year-old cousin. She is the tiniest thing ever.
Sure.
Would she just like go down, or would she float?
So it depends on her density. So her volume is not very big, right, since she's so small. But she might be very light because she doesn't have as much weight to her. So because of that, she might float easier. But if she was really dense, density in humans usually comes from the muscle. So muscle is more dense than fat is. So if you have a lot of muscle, it's harder to float. Whereas if you have more fat, then because that takes up volume, but it's not as dense, it's easier to float. So your cousin will probably sink very easily because she's so small. Any other questions here? Yes, sir. Huh? And we resume the video. Yeah, if there's no other questions.
got up the size and direction of all those arrows, a bunch of stuff cancels out, and you're left with one net force pointing upwards. That is the buoyancy force. And if your buoyancy force happens to be greater than your force from gravity, you float. And if your buoyancy force happens to be less than the force from gravity, you sink. Now we usually think of buoyancy with water, but you can think of things like helium balloons being buoyant in our atmosphere. So here's a trick question. Which of these has a higher buoyancy force? It's actually the rubber ball. Buoyancy force has nothing to do with the density of the object, just the volume. So since the rubber ball takes up more space, it has a higher buoyancy force. But, you might object, then why does the rubber ball sink and the balloon floats? Remember, it's a tug of war. The rubber ball sinks because the force from gravity on the thick rubber skin and the air inside is bigger than the buoyancy force. But for the balloon, even though it doesn't have as big of a buoyancy force compared to the ball, it still floats up because that buoyancy force is bigger than the weight arrow from the helium and the thin rubber shell. And the helium will keep rising like a ball floating up from deep in a lake. And then it will eventually hang out where the density of the atmosphere is roughly equal to the density of the helium in the balloon, because that's where the tug of war becomes equal. Whew, we made it through. Now back to my nephews.
He's stuck in there now. And so this is kind of a silly way, but this is a really good example of how vibration can change things a lot, okay? So it's something you need to be very aware of if you go into engineering or into material products like that. Because like they said, there's a couple of ways that vibrations are being used right now industrially, but there's a lot more ways that they could be used, similar to things like this. So as you increase the vibrations of something, whether that be the drill that you're using to find oil or water, the vibrations in your car so that it doesn't shake to pieces, or the vibrations in buildings bowling ball that he's holding under there is now pretty well stuck. Okay, it takes a lot more force to move that ball now than it did before when the air was going through. So that should be it. There you go. Any other questions on vibrations? We are out of time. You guys have 7 minutes. We have to go. So, yes, ma'am.
What's that 15 times yellow pool? These vibrations?
There's probably vibrations